Hello everyone. Let's check important properties of random variables. So we have two important properties. The first one, it is called sum property. And second one, it is the product property. And talking about sum property, we have the formula here. Expectation with respect to the linear combination. Then we will have for the result. Actually, it's a linear combination with respect to the expected value. All right. And the second one about the product property of the expected value. So we have the product form here. It's pi. All right, it's pi. Pi means the product. However, for this one, we have the specific property. Only when we have a stochastically independent random variable, then we have this. So in the following, let me have an extra page to illustrate the two properties. First one, this one, sum property. So we have these. So we have AI, XI. And so that we have summation and AI with respect to the individual expected value. This is a sum property. Sum. All right, sum property. To get this, actually, we should have the definition for expectation. Talking about expectation, perhaps I may have a lot of things to review for you. So first of all, this one, talking about expectation. So for example, this. Only x. So how to have the result? If I have a discrete random variable, so later I already have, continuous. Continuous random variable x. So we have these. Summation we assume for the entire range. So it should be x. Alright, so if we have a single variable, then we have the expectation with respect to a continuous random variable. Previously, we have the result if we want to focus on the expectation for a single random variable. And how about a function? So if we have a function, then we will have these. This one. If we have a function, then we have these. G of x. And g of x, in fact, we still have almost the same form. But the position here is g of x. And we won't change the others. Alright, so if we have a function, g of x, so g of x here. So you look at these. Same, we have the PDF for the continuous random variable x. Well, so this is a case for a single random variable, so that you have the expectation. But right now, we don't have a single random variable. We have multiple random variable. Alright, multiple random variable from 1 to xn. So we will have the join PDF. So here I already have a join PDF first. Alright, so if we have this, how to define the expectation for a function? Here I mention function explicitly. So if it is a function, it should look like this one. G 1 2 to xn. So how to have that? Actually, we should have a multiple integral. 1 2 to n. Alright. So I don't have the range here. Negative infinity to infinity. I leave them empty. But where we have a function here, we have a function gx1 2 to n. And then we need to multiply the joint probability density function here, fs1 2 to n. And here s1 to sn. And here integral, so we have a dx1, dx2 to dxn. Alright, so about the multiple random variable, in fact, we should have multiple integrals, and so that we have the result to have the calculation. So let me emphasize this. We have a function here and function here. And also we have the same joint PDF. Alright, so join PDF, then we can have the result. But why I want to mention this, if we have this, actually we need to pull something. For example, right now, we need to check. If we have a single random variable, say it's x1, based on this definition, perhaps I call this is definition 2, and this is definition 1. If we start from definition 1, if we start from definition 1, and if we start from definition 2, only focus on a single random variable, can we reduce to the same result? So right now, let me have the results for you. So let me erase some. Alright, so maybe I have some result, but I erase also so that it will be easier for me to derive further. So I just want to mention, okay. How about we start from definition 2? However, we just have a single random variable, x1. x1, actually, we have an integral from 1 to n. Alright, so however, we have a function here, x1, but we have x1, x2, xn, x1, x2 to xn. And here we have a dx1, dx2 to dxn. In fact, I ignore the entire range. But right now, I have the entire range. We have 1 to n. And so for this one, can we reduce to definition 1? Here, I just want to mention this. And so that I want to let you know, for the current definition, joint PDF can reach the expected value. Is it true? Can we reduce to the original definition? Here, I just want to mention that. For this, in fact, I try to rearrange the integral because of x and x. So let me have change the integral because of the entire range. So I try to move this one to the outside. Alright, so because of x1 to the outside, so we have this form. And for the remaining, actually, I try to have a different color. So it's 2. So moving to outside, so here, same. I try to move this one, x1 to the outside. All right. And we have the other, so we have x1, x2 to xn. So x1, x2 to xn. And here I try to change the actually we should have a multiple. All right, so that we have a dx2 to dxn, but multiply dx1 only. Well, if so, I want to ask you this equation. The inner side, what is the equation for this one? Okay, so the inner side, actually, it should be this. So it's true. dx2, dx3, dxn. Why we have this result? So we should have the interpretation. The interpretation here, this is PDF of x1 simply. And here, look at this. We have a joint PDF. But right now we have the integral with respect to 2, 3 to n. All right, 2, 3 to n. What that means, if we have the integral, that says we try to have the integral considering all factors regarding x2, x3 to xn. If so, performing the integral, that says we try to have the probability for all partitions. All right, partition based on x2, x3, and xn. And so this is the total, something like try to find the total density probability, or maybe probability density, sorry. And so that is this one. If it is this one, then we can replace this one by this. x1, oh okay, here it can be reduced to 1 only, and this one x1, and dx1 if we have the inner side to have the proper derivation or interpretation. And so then we have this result. All right, so for this one, I just want to emphasize starting from definition 2. In fact, we can reach definition 1. So of course, this definition is very generally, and so that we can pass on the general description or the general definition here. If we have the general definition, then we can start for the remaining. Here, this one. Oh, okay, right now we have the function sum. It's the linear combination. All right, so here I have 1 to n. If so, we have this multiple integral. And I forget all the details, just have this. So we have x1 to xn and dx1 to dsn. All right. Well, if so, what to do? Actually, we try to exchange the position. So the position move it to the outside. Here we have I to equal to 1 to n. To the outside, but for the inner side, we have this. Xi, here we still have this 1 to n, 1 to n, and ds1 to dsn. Well, so what it means, oh, okay, here we have the individual xi, but we use join PDF. And previously, I didn't know, even we have the current way to show the result. Okay, it's simply, this is the expectation for a single one. And this one actually equal to the results using definition 1. So, of course, we have this one, AI, but for the remaining, actually, it should be the expectation regarding xi simply. And here the definition follow definition 2, but actually we can use definition 1 to have the calculation. I pull that for you, and so that is still okay and valid. And finally, we can have the property. Right? This is the sum property. All right, so this is a proof for sum property if I use continuous random variables x1 to xn. All right, and likewise, you can use the concept for the discrete random variable starting from x1 to xn, and you still can have the results. All right, so this is the first one, and let me check the next one. Product property. And product property. And product property, actually, we should have the condition. Oh, x1 to xn, they are independent. All right, so independent means, all right, so x1 to xn, the joint PDF x1 to xn should equal to the product form x1 multiply xn, sorry, this one. All right, if so, think about this. Likewise, the product form pi from 1 to n, it's xi. And then we have the form, same, multiple integral. And here we have a pi. And it's xi. And this time we have this, sorry. This one. We have x1 to xn, x1 to xn, and ds1 to dsn. All right, because of independence, so we can apply the property here. And move the product to the outside, so we can rearrange to this form. Pi, starting from 1 to n. And here we have a multiple integral from 1 to n. And because of the property here, so we have xi. x1, xn. Actually, it's x1, x2 to xn. So d actually should be ds1 to dsn. So let me look at this. All right, so here maybe let me remove this. So actually it's x1 to xn. If x1 to xn, so we have this. It should be x1 ds1 multiply. Here we have xn and xn dsn. And so that this is the expectation. Oh, it's the polar form. Finally, let me use this color. It's a polar form, this one. It's expectation with respect to 1. Expectation with respect to n. We have the polar form, so finally the form should be pi. Alright, so we have the product property. Alright, so that'll check the property again. This one. Alright, so actually I remove this because if I use pi here, it is not easy to see how to have the individual expectation. So I remove this one and replace by this one. It's polar form. Alright, but we separate to the individual one, 1, 2 to n, and so that it's the polar form of the expectation. So we have the product property. Alright, so this is the important property regarding sum property and product property. And for the two properties, actually I use continuous random variable. Random variable, and we can prove it. And likewise for the discrete random variable, even not the same way, but actually we can follow the discrete notation to have the corresponding deviation, and so that we won't use the PDF. Instead we use PMF, and still we can have the result. Alright, so I use one possible random variable, the continuous random variable, to illustrate the two properties. Alright, that's it. So this is the property of the sum property and the property of a product property. And next one, we have this property. Sum property of variance. Previously, it's the expected value. Right now, it's variance. So variance, actually, we should define variance here. What it means, variance should be this. Variance for a single random variable. A single random variable, how to define variance? Actually, it should be this. Alright, if this, then how to have the property for a single random variable? This one. All right, we can expand. So we have this x squared. And here we have this. Right? And also we have this. All right. And we have this. And you can look at this. Oh, okay. About all the equations here, it's a single one. So single one, can we have the separation? Sure, we can have the separation. How to have the separation? You can use, for example, continuous random variable. Continuous random variable says, oh, okay, we have this. We have x squared and minus this. And plus this. And using single random variable and dx. So this actually it's this. All right, and minus this. And in fact, this is a constant, so we can move it to the outside. And we have these. And for the final one, this is a constant as well, so it's constant. So it is. We have this integral. And so let us check, and so that we can have the results. And this one, this is the total probability is 1. Alright, PDF. And for the whole range, from negative infinity to infinity, so it's 1. So finally reduce to square itself. And this one, what's this? Actually, it's x itself. And this one, right now, if we want to have the operator e, and it's x squared. So for this one, in fact, I have the final one to have the property through expansion. Even it's not linear combination, but if we have the function here through sum or substrate and so that how to have the result. Oh, okay, this one. Finally, the first one is expectation respect to square. And second one, actually, we have a constant here, 2 expectation with respect to e. And still have the expectation, this one. And finally, we have a plus itself. All right. Well, this one, square and square, plus 1 minus 2. So finally, we have the result. Oh, okay, this one. It's square expectation minus this. So first of all, for the property of variance, and consider a single random variable, we should have this. All right. So consider a single random variable and try to derive variance. This is the formula to derive variance. And to derive variance, actually, we need to have covariance along with the covariance so that we can have the variance if we consider multiple random variables. So right now, let us consider this one. Covariance. All right, if we consider covariance, then we have these. Covariance. So here we have a covariance. For example, x1 and x2. Covariance, how to have a covariance definition, follow this. This is a definition. Oh, cross correlation. Or the cross product form. So it's all same. We want to have the expansion. And this. And here. Likewise, we can try to consider all are continuous random variable. So likewise, we can have this directly. So this time, I skip the PDF and derive the result to the next stage as this one. Oh, okay, it should be this. And here, this is a constant, so we have a constant, so that we have this. It should be this expectation again, and minus expectation. And plus expectation with respect to all right. And here it's a constant. And this one is a constant. Based on the sum property. We have this. Or we can move the constant to the outside, move constant to the outside. And so that we have expectation with respect to x2. So we write it again. Move it to outside, and so that we have expectation again with respect to 2. And likewise, this one 2 and 1, so it's 2. And finally, plus 1. We have a product form for 1 and 2. And we write, so we have cross minus 2, but plus 1, so minus 1 only. Alright, so if so, then we have the result. And this result follows this. So actually, we should talk about property of variance. But we don't know, oh, variance. And how about covariance? And so then we have that. And right now, if we want to follow the property, some property to check some property for variance. And this one, we have a linear combination again. But linear combination, in fact, we should have the definition. Let me have the way to have the derivation for you. All right, so we want to have a variance, this one, linear combination. And so then we have the definition. Oh, this one. And minus its expectation. All right, minus expectation, but raise to power of 2. So if so, how to do? First of all, let us apply some property here. Some property, so we have these. Alright, so we have some property of expectation. If some property of expectation, then we have the results here. Oh, we have these. Square, but right now we can have the derivation. Alright, so we have the form like this. If we have n random variable, 1, 2 to n, and if you can have the further derivation, then we can have the results. This one. We have a variance, sum of a variance individually, but we raise the coefficient to square. However, we have the cross term, it's covariance. Previously, we didn't have the definition for covariance. How to have these results? Actually, you can pass on the expansion. Alright, expansion of this. So how to have the result? Actually, we should have the form. AI xi minus its result. And we have sum of this and multiply sum of that. So let us have a different way to express this if we have the variance. So the cross term should be this one. Let me erase O. So the cross term actually is square. So the square actually we have this one. We have A1. X1 minus square. Oh, sorry, minus itself. Alright, plus A2. X2. So this is the previous result, and to xn and square, so we should have multiply A1 again, A2 and AN Alright, because of multiplication, so we should have the result. So look at this. So we have the result. Oh, okay. Focus on itself. We should have the first one. It's A1 square and X1 square. But for the remaining, it should be summation. One multiply the others. So how to have these? It should be this. A1 summation I from 2 to n AI. And here we have these. The outside should be, or maybe I can write it inside X1 itself. And we have this. Xi minus Xi. Alright, so here. And 1 here. And likewise for 2. 2 here. So first one, we have multiplication. And second one, we have multiplication. So we have a2 squared. And here it's a2. And I rewrite here maybe from 1 to n, but I is not equal to 2. And here I is not equal from 1, but I is not equal to 1. All right, likewise, we have an. And plus this an summation. And here I is not equal to n. This one is ai. All right, so collect all of these. So look at this, let's check these. So we have a sigma ai squared here, variance. So it says variance, where we have a variance, we have the cross term, but we need to have expectation. Cross term and expectation. So that we have the first one collected. We will have these. I use a different color to write all this. Okay, about this, actually finally we have these. AI squared. Here it's variance squared. And we have a summation. So summation. Sum. Sum, then we have the results here. It's correct. And we have 2 A, IJ, and covariance. So here, actually the second term, it's sigma aij. And actually we have this one, E. So this is covariance. All right, and we have a covariance x1. And xi here, covariance x2 and xi, covariance xn and xi. And you can rearrange it. So we have a 2. Should we have a 2? All right, so should we have a 2? If we have, for example, 1 and 2, and here we have 2 and 1, we can collect that pair. So actually we have 2. And finally, rewrite it, collect them, we have the results. These results, I didn't know we have a covariance, but we need to collect them by pairing, so we can squeeze 2. But finally, squeeze out, so we simply have I to n minus 1 and j larger than I. And so that we have the remaining and show the covariance. So this one actually equal to this. So this one says equal to 2 summation I from 1 to n minus 1 and summation j equal to I plus 1 to n and covariance aij and covariance ij. So you can check it, this one. So in fact, correct. But the limited space, I cannot have the detailed derivation. And actually, I show you this, it's correct. So up to now, I already have the property. If we have some property for covariance, yes, this one. If we have this one, how about if we assume all covariance are 0? If all covariance are 0, then how to have this? Independent, then we have this. Oh, they are uncorrelated. Uncorrelated. Uncorrelated says, oh, okay, covariance is 0. Uncorrelated. So the current one, actually, if they are uncorrelated, then we can have the result. How to have the result? Oh, okay, for all values, they are 0. And they are 0, so we just have sum of the variance. Well, so if we want to have some property of variance only when we have independent or uncorrelated, then we can reach the property. The property, look at this, AI within the linear combination. By linear combination, we have AI square. Alright, so this is the sum property of variance. I already have the property of variance, and also already have the property regarding the linear combination. And so that generally speaking, we should have the general form. The general form may be found. You can pass on the current equation to find the pair. Alright, so can we have the pair? Actually, yes. But how to have the pair? We write the results into the notation. Because of that, we need to have a covariance. I already have a covariance. And here we can have the reduced result if we have the assumption of independence and uncorrelated random variables. Alright, so that's all. I use this way to identify how to have the derivations. And finally, for the remaining property, actually you can find advanced result, and so that you can have this property. We want to get distribution of sum. Alright, distribution of sum. So this is the case here. If we want to have sum of this, how to have the result? Actually, we can find the area. And we use double integral. So double integral here, we have actually we have the result. Alright, and this result, how to have the CDF, cumulative distribution function, this one, CDF. So CDF actually find this Z. And Z lower than this. For example, we have sum Z, right? So sum of Z, it should be this. Alright, and lower than, so we should have the result. And we should have the region here. Double integral. Alright, and using a joint probability, then we have the result. Using the region. And the region here, why we have this new region? Look at this. Look at this. We have the region, actually region from this. Oh, we are showing y allowed to negative infinity to infinity. But how about x? Actually should start from this. Why? So x equal to so here actually if we have this one, so x actually from negative infinity right to z. So if we have the proper correction, we have this one, z. Oh, sorry, maybe I should change it to a new form. Rewrite this. So actually we have the form. Consider this special case. Actually the special case here. X plus y equal to z. So the region here should be if we have x first. Sorry, if we have x first, we assume from negative infinity to infinity. So x here, but y actually should start from this one. So x first, sorry, x first, so I need to change it, sorry. Let me have this again. X equal to negative infinity. Negative infinity to this region. So actually, if we have x, actually negative infinity to x equal to z minus y. And for y, actually the entire one, so correct and correct. So if so, we have this result, negative infinity to infinity. And this one to z minus y. And we have a joint density function. And joint density function, this one. How about the CDF? CDF, we should perform differentiation. So differentiation regarding the CDF, it should be this. Oh, okay, we have a variable here, and using chain rule, differentiation, and chain rule. So differentiation with respect to the inner side, z. So z actually we should have this differentiation. Perform differentiation with respect to z. dz to have this one, PDF z. So we have this. And this one actually we can perform dz. So the outside same. dz here. Z minus y. Alright, and dz here actually you can use chain rule respect to the variable. So respect to variable z minus y, so it's first one and multiply dz, so it's 1. So finally we have the result. We remove this if we perform differentiation. So we have this one unchanged. And through differentiation, this one using the theorem of calculus. So we have this. This is a position for x. So x should substitute this one into. So we have z minus y and this one y. And dy, if we perform differentiation and using results of theorem of calculus. So we have this. So look at this integral and join PDF and z minus y, and perform integral with respect to y. So can we have the result here? Here, this one. Before we have the independent, actually it should be this one. Previously, the derivation should be, oh, okay, this one, z minus y. And through the differentiation, we should have this. And we have xy, z minus y, and y, and dy. And likewise, we can have some further derivation, but if I have this, actually this one, z, this is the z of z. And likewise, we have this form, but we have independent, so we have this. Z minus y, and x, sorry, this is y, and y dy. Because of independence, so we have the polar form. If we have y itself, so we have x, z minus y. And actually, you can rewrite in terms of x, so we can have the result x, z minus x using y, x itself. So this form or this form, if they are independent. So about property of sum through the region. And through some derivation, actually we should have a formula, this one. So special, we have a special case z plus 1. We will have the result. And if we don't have the special case, actually we should have a region phi z. And you can find a suitable region to have the integral. Then you will have the result. All right. So that says we have this result. And likewise, how about independent and non-negative? Actually, non-negative, we follow the form here. So previously, I have the derivation for general one. It doesn't mean we have independent, but the general one, we have this. Z. We should have the form in terms of y. So we have z minus y, and y and dy should be this form. And right now, we are showing they are non-negative. All right, non-negative that says, oh, okay, the value should be greater than 0, greater than 0. And this one greater than 0. So we have the result. Oh, okay. The range for y should be larger than 0, smaller than z. So actually larger than 0, smaller than z. But this time we have s. But actually we have a new form, 0 to z. But we have y, so we have x. Y, z minus y, and y dy. So likewise the same. Y. And likewise the same if we have the independence, and so that we have the polar form, but this time we have x only. Alright, so this one we have a property of a random variable if we consider distribution of sum. Distribution is CDF, but finally we have a PDF. And finally we have a PDF. So I try to have this way to that have the important property of random variables.